Hi everyone. In this video, I'm going to show you how to do an AC analysis on a CE transistor amplifier shown on the left here. And we're going to derive some expressions for ZI, ZO, AV, and AI. So ZI means input impedance as seen by VI. ZO is the output impedance as seen by VO. AV is the voltage gain, and AI is the current gain. All right, so when we do AC analysis, the first thing we should do is there's a couple of steps we need to do. First of all, we should short all capacitors. See down here, I put down some notes about what you need to do. So first step is to short all capacitors. So because we're assuming that at the relevant signal frequency, all the capacitors have negligible impedance. All right. So that means for now, we're assuming that there are 0 ohm. So meaning this C1 becomes a short, C2 also becomes a short. All right. The next thing we do is we zero all DC sources. So in this circuit, there's only one DC source, and that's this VCC. So that needs to become a 0. So instead of VCC volts, it will be 0 volts. All right. So which means that if it's 0 volts, it means that the top part of RB and the top part of RC now ends up as the ground. So the RB will have one end on the base of the transistor, the other end will be connected to ground. And similarly for RC, the bottom part of RC is connected to the collector, and the top part of RC will be connected to ground once we do step number 2. And in step number 3, we have to replace our transistor with, one of the models. In this case, I'm using the RE model. Just to remind you guys, so this is what an RE model looks like. It has the base, it has the base, that's the base side, that's the collector side, and down here is the emitter side. It has a beta RE, it has a beta IB, it also has an RO. All right, so this is the RE model for a transistor. Okay. For a common emitter transistor arrangement. Okay. So once we do all 3 steps, we should get a circuit that looks like this here. You can see on the right there. All right. So as I mentioned earlier, C1 and C2 become short, so they're not here anymore. RB and RC, the top part becomes ground, so that's why RB ends up. The top part of RB ends up ground, so it ends up at the bottom. And the top part of RC also becomes ground. The other side is to the collector. There's RC. Top part is connected to the collector. The bottom part is connected to ground. And then the transistor is replaced by this RE model. All right. So we need to go and figure out what ZI is, ZO, AV, and AI. So let's do that. Okay, so ZI is defined as the input impedance as seen by VI. Well, ZI is just basically resistance impedance. So again, using Ohm's law, R equals V over I. V over I, in this case, V over I is VI over II, right? So let's just write that equation first of all. Sorry. All right. So we're talking about input impedance all right, so that's going to be ZI. Z of I is going to be simply using Ohm's law, R equals V over I, so that's going to be VI divided by II. All right, so that's the current going into the components to the right. All right, so that's what ZI is. So now we need to go and figure out, what is VI? What is II? What is VI? Well, if you look at IB here, now IB is a current that just flows into beta RE. All right, so we can actually write an expression that links IB with II. Okay, so what is that expression? If you notice, II comes in here, and then that current gets split between RB and beta RE. So this is so if you want to write an expression for that links II, IB, RB, and beta RE, it's basically a current divider. All right, so we just use the current divider equation. So input impedance ZI. So next line, I want to say the using current divider rule. All right, so then we can write in terms of IB. All right, so IB is going to be equal to the total current, which is II in this case, multiplied by RB. All right, multiplied by RB divided by RB plus beta RE. All right. Sorry, beta RE. All right, so that's from the RE model. Okay. So that's our expression for IB. Okay. So that's IB. And because from this equation, therefore, you can actually figure out what II is. All right. Therefore, if I want to write an expression for II, will be II is going to be equal to IB. Right? I'm just moving this side from the right side to the left side. So the top part will be RB plus beta RE. All right, all divided by RB. All right, so that's our expression for II. Okay, so now what about VI? Well, VI is the voltage that is across RB, and is also a voltage across beta RE because these two resistors are in parallel. All right, so you can write an expression for VI in terms of IB and beta RE. All right, so let's write an expression for VI. So since V underscore I is also across beta RE, right? Beta RE, we can write VI. We can write so V underscore I, V equals IR, right? So I is IB, all right, multiplied by V equals IR, R is beta RE, so that's just beta, and then RE, all right? All right, so now we have an expression for VI, and we also have an expression for II. So to work out ZI, you just one divided by the other, all right? So so I can write ZI. So ZI is equal to VI, which is this one here, right? All right, that's that one there. So ZI equals that. All of it divided by II is all of this. So so at the bottom there's going to be well, I'm just going to write. Let me just write everything down first. I underscore B IB times RB plus beta RB. Sorry, beta RE. All right, all divided by RB. All right. All right, so that's what that is. And you should notice that by doing this, the IB cancels out, and then this capital RB ends up at the top. So you're gonna get the expression of beta RE times RB, all divided by RB plus beta RE. All right, and so that's our expression for ZI. Okay. So are there any simplifications that can be done here? Well, it depends. So for example, if But you know, if we keep it as it is, this is a more or less a complete expression for Zi. But if you can imagine that if beta Re is very much smaller than Rb, all right, if beta Re is very much smaller than Rb, then the beta Re at the bottom becomes insignificant. Then you're left with just Rb at the bottom. So if you're left with just Rb at the bottom, then both Rb at the top and the bottom will cancel out. Then Zi will just simply be beta Re. All right. So let me just write that. If beta Re, so if beta Re is much smaller than Rb, all right, then Zi is just going to be equal to beta Re times Rb all divided by just Rb, right? All right, so since Rb top and bottom will cancel out, so Zi will just become beta Re. So that's the simplest version of Zi, if you like. All right, that's assuming that beta Re is much less than Rb. Okay, so that's Zi done. Let's move on to the next, which is Zo. So what is Zo? Well, Zo is the resistance seen by Vo going towards the left. Now, whenever we do an output impedance, we must always zero the source. All right. To derive Zo, we must always zero the source signal. All right. So to derive Zo, we must always zero the source signal. So in this case, when you zero the source signal, which means Vi here, if that is zero, then the top part and the bottom part will be now connected. All right. So that means the top part and the bottom part will have the same potential. So therefore, there won't be any current flowing. So IB would be 0. All right. Okay, so when IB equals 0, then you're going to get beta IB also 0. So if IB is 0, beta IB is going to be 0. All right. So which means when you look at ZO looking in, you're just going to see an RC and R naught being in parallel. Right. All right, so to derive Zo, we must always zero the signal source, the source signal. All right. As a result, IB equals 0. It's going to be equal to 0 amps. All right. All right. So when that happens, then okay. Therefore, beta IB will also equal to 0. All right. All right. So beta IB equals 0. All right. So meaning that our output impedance ZO will simply be, as I said, RC parallel with little ro. So it will be RC parallel with a little ro. All right. So that's the complete expression for what ZO is. Okay. Now, if another common things that people would equate, if RO is much bigger, you know, more than 10 times or more than RC, all right, then our expression for ZO will simply be equal to RC, right? Because remember the RC and RO are in parallel. So if RO is very big, then it will cease to contribute to the overall impedance. Then it'll just become RC. All right. Okay, so this is, well, okay, these are all approximations, of course. So approx. All right, so approximately RC. So same with the ZI. So it's going to be approximately beta RE to RB. So approx. Right, and so is this. All right. Okay, so now we have expressions for ZI, we have expression for ZO. All right. Okay. All right. So so now we have ZO and ZI. Now we need to figure out what AV and AIs are. So first of all, AV. So voltage gain is defined as so that's AV is equal to VO divided by VI. All right, so that's what it's defined as. And then we can write VO using Ohm's law. V equals IR. So VO is here. So VO is over there. I is actually in the, see, IO, because VO is positive pointing up. So, which means that the current needs to be positive pointing down. But since IO is pointing up, so we need to do a negative of that in order to get a current that is pointing down. So you're going to get a negative IO multiplied by ZO. All right? So that's the output impedance. All right? So this is just Ohm's law. And then, and for VI, VI is simply equals to, okay, VI is on this side here. Again, using Ohm's law, it's just going to be II times ZI. All right? So II times ZI. Oops, sorry. ZI. All right. Oops. ZI. Okay, fine. All right. So that's our expression for VO and VI. So we need to go and figure out what is IO, what is II, because we already have ZO and ZI, so we just need to figure out what IO and IIs are. All right. So to work out what IO is, well, we already have II, so we just need to work out what IO is. Well, IO is, if you look at this, it's a current that is going up on the RC branch. But if you notice this, the entire right-hand side, there's a current source, a dependent current source of beta IB. So beta IB is a current that flows down and then goes up to both of these, and then combine again at the top, and then return back to beta IB. So we can write an expression for IO in terms of beta IB and RO and RC as a current, using the current divider rule. All right. So using the current divider rule, we can write an expression for IO. All right. So IO is going to be equal to the total current, which in this case is beta IB, so it's beta IB, multiplied by the other resistance, which is RO, divided by the sum of the two resistance. So it's RC. All right. Okay. So that's our expression for IO. Okay. So we now have enough to work out everything, because we have ZO, we have ZI. Now we just got IO, and of course we have II from up there. So now we can work out what AV is. So voltage gain AV, all right, is just VO over VI, where VO is negative IO, ZO. All of this divided by II times ZI. Okay, let's put in brackets here. Let me see. All right. Okay, that works out. All right. So now let's just substitute all these things in. All right. So it's going to be negative, and then the top part The top part is going to be IO, which is this term here. So I'll just copy that. All right. Times ZO, which is this term here. Oh, I'm going to expand this RC parallel RO and expand it into the expanded version, which is going to be basically RO times RC, all divided by RO plus RC. All right. So that's just the parallel term expanded. All right, and then all of this is divided by the bottom part, which is II, and II is we did it before, which is all of this. So I'm going to copy all that. All right, so I is all that times ZI, which is all of this. All right, so I'm going to copy all that. Put it here. All right, so put it there. Okay, so close that. And all right, so now we look at what terms will disappear. Well, we can see that IB will disappear, so let's just highlight those. So IB will disappear because it cancels top and bottom. There's IB on both top and bottom, so IB down here will disappear. All right, and then what else will disappear? Well, you have RB plus beta RE. You also have RB plus beta RE here, so that will also disappear. All right, so that part is going to go, and so will this. All right, so that's gone. RB will disappear because there's an RB term there and an RB term down here, so that's going to disappear. And so will this RB. All right, so it'll cancel out. All right. Well, there's a beta term up there and there's a beta term down here, so beta will disappear. All right. So beta will disappear. All right, so beta will disappear. Okay, so what are you left? What are you left with? Well, effectively, you just have an RE at the bottom, but then you have all those terms at the top. So let's just write that out. So it's going to be negative. Oh, sorry. So it's going to be negative RO squared. All right. All right. So R squared multiplied by RC divided by RO squared. Sorry, RO plus RC squared, all squared. All right, all squared. All right. So that's the top part. All of this is then divided by, sorry. All right. So this is what I have left: R squared over RC, and then divided by RO plus RC. Now, all right. So this is the expression we got for voltage gain. It looks a bit hairy, but if you notice, typically RO is actually very, very large compared to RC. All right. So typically RO is very, very large compared to RC. So as a result, RC would be insignificant. All right. So typically R naught or RO is much, much bigger than RC. So therefore, we can simplify the expression a bit for AV. All right. So if R naught is much, much bigger than RC, then it means the RC term is going to be insignificant, and all you have left is just going to be RO squared. And that RO squared can cancel out with the RO squared at the top, and what you're left with is just RC divided by RE. So therefore, AV will just reduce to RC divided by a little RE. All right. Okay, so that's the expression for AV. Now for AI. Well, let's have a look at AI. Well, the current gain is defined as AI is simply equals to IO divided by II. Oops, sorry. Underscore I. All right. All right. So we already have expressions for IO, which is here. We also have expression for II, which is there. So we just have to put one over the other. So this is the full thing. So it's going to be equals to so it's going to be equal to, I'm just going to put a bracket around the whole thing. All right. All that divided by all of this. All right. So all that divided by all of this. All right. So that's going to be equal to what? Well, what cancels out? Well, you can see that IB cancels out. All right. So let's mark those. So IB will cancel out with top and bottom. All right. So IB will cancel out. Okay. Will anything else cancel out? Doesn't seem to be. So therefore, what you're going to left with is beta at the top there. Beta times RO divided by, sorry, RO divided by RO plus RC, right? And all of that is going to be divided by, sorry, and then this RB at the bottom there will end up at the top. So it's going to be times RB, all right? And all that divided by, in bracket, RB plus beta RE, all right? So beta RE, okay? Okay, so that's the expression that we have after crossing out a few things. Well, again, we can look at simplifying this. So, for example, typically for RO, it is typically very large compared to RC. So then what you'll have at the top there is RC becoming insignificant compared to RO. So then the RO will cancel top and bottom. That's one. The other one is beta RE is typically much smaller than RB. All right, beta RE is much smaller than RB, so which means that the beta RE part will become insignificant, then the RB will cancel out. So what you'll have is eventually is just beta. All right, so typically you're going to get RO is going to be much larger than RC, and also beta RE is typically much smaller than RB. All right. So therefore, our expression for AI is going to simplify to just beta. All right, and that's the final answer. Okay. So hopefully this gives you an idea of how do you do a full AC analysis on a typical CE amplifier. Just to recap, you need to convert your initial circuit into an AC equivalent, yeah, by doing these three things. All right, and eventually you end up with a circuit like this. And then with a circuit like that, you start working out what are expressions for II, IO, ZI, and ZO. Once you have those four things, then you can start working out what AV and AI is going to be. That's AI. All right? Okay, thanks for watching. Till the next video.